So, now we will see an application in this lecture, we see an application of that compactness result, and this is regarding equivalent norm. In fact, there will be many norms. So, in H1 omega. So, in the study of PDE of second order, especially of elliptic type, so, so PDE, so this I will just write formally. So, del square u by del xi xj plus lower order terms in some domain omega, and u given u are normal derivative. Okay. So, this will be the trace, okay, and we will be seeking solutions in appropriate Sobolev spaces, and it is important to take these coefficients into account and try to define an equivalent norm in that Sobolev space, so that we can apply either Rees representation theorem or Lax-Milgram lemma as the case may be. That we will see in the next course. So, now because of such equations, so we look for some equivalent norm in H1 omega. Okay. So, some notation again. Okay. So, let P be this matrix function P I J x. So, P I j equal to P j I, P I j belongs to. So, these are continuous functions in omega closure. So, they are bounded. Okay. So, we also see this is symmetric matrix, but we will also put a positivity condition. So, this matrix okay. So, assume there exists gamma positive such that, so P I j x j j or I j, so bigger than or equal to gamma j square for all j in R n and x in omega closure. Okay. So, this comes from this ellipticity condition of the second order PDE. Okay. So, typical examples. Okay. So, simple examples. So, P is a scalar matrix. So, P is just some function identity where P is in C omega closure and 0 less than gamma less than or equal to P x some bound. So, call it P infinity. So, this is typical example. So, you take a scalar matrix. Okay. So, we also consider two more functions. So, let Q be again a continuous function and Q non-negative, and R is a function, continuous function defined on the boundary, and R is also non-negative. Okay. So, consider this bilinear functional, bilinear form. So, W F G, I will put that. So, this is summation I j equal to 1 to n integral omega p I j del f by del x I del g by del x j. So, this is integral over omega. So, this term contains only the derivatives of f and g. So, now we consider over omega this q f g, okay, and then a boundary integral. So, this r f g. So, let me write that ds. Okay. So, that is surface measure on the boundary, and these are, remember, trace. Okay. So, where this is defined, so for f g in h 1 omega. So, each of these three terms is finite, as we have seen earlier. So, these are traces. So, these are both in L2 of d omega. So, this integral is finite and r is continuous, non-negative. Okay. So, this is bounded, and all the three. So, this bilinear. So, you can check that. So, it is linear in each of the components f and g. Okay. And the norm, so this is a new norm. So, let me write that triple norm. Okay. So, this is equal to W f f square root. Okay. So, the theorem there exist positive constants C1 and C2 such that C1 f in h 1 omega is less than or equal to this triple norm, and again for all f in h 1 omega, provided, okay, so this important condition, either r is not identically 0 or q not identically 0. Okay. So, remember, q comes here and r comes here. So, we cannot take both of them simultaneously 0. Okay. So, this is an important result. So, in the language of functional analysis, so we say that this triple norm is equivalent to the H 1 norm. So, one part of the proof is almost trivial. Okay. Okay. So, proof. So, the easy part, okay, just look at WFF. Okay. So, here we can just since these are continuous functions in omega closure, they are bounded. So, Q is also bounded and R is bounded, and here we use the trace theorem. Okay, so that is important. So, just to note that. Okay, so we have, this is important. So, norm of L2 nu omega is less than or equal to constant f in H1 omega, okay, for all f in H1 omega. So, where this is the trace. Okay. So, this immediate, once you use that, so you immediately get that this is just some constant f in H1 omega square. Okay. So, this is easy part. Okay. So, that implies that. So, this part is easy. So, the other part is bit difficult. So, let me, and how the, so here in fact we do not need any conditions on Q and R. Okay. In this is bounded. So, we need only bound, okay, nothing else. So, this other condition becomes relevant in the other part. Okay. Suppose the reverse inequality does not hold. Okay. So, we will try to get a contradiction using this assumption. So, what does this mean? Okay, then we can choose. So, these are standard arguments in functional analysis. We can choose a sequence Fm in H1 omega such that this W, let me write that, okay, this Fm in H1 omega square is bigger than for m equal to 1. Okay. Because this is, if the inequality is true, means what? So, this norm of f in H1 omega square is less than or equal to some constant WFF. So, if that is violated, then we should be able to get this sequence. Okay. So, put GM, these are again standard techniques in functional analysis. I am not doing anything extra here. So, this implies again GM is in H1 omega and norm of GM in H1 omega is 1. Okay. So, this GM is a bounded sequence in H1 omega, and using the linearity of this bilinear form W, further this W GM m is less than 1 by m. Okay, so let me write there are 3 terms in WGMM. So let me write that. Okay. Thus, so let me write that. So this summation ij omega Pij del Gm by del Xi del Gm by del Xj plus omega Q Gm square plus del omega R Gm square. So this is less than 1 by m. So from the positive definiteness, so this is just I will just this is bigger than or equal to gamma, maybe some constant. Okay, so that does not matter. So we get grad Gm square. I think you exactly get that. Okay, so this is just Qgm square and Rgm square. Okay, so that means what? So we have grad Gm square or omega is less than 1 by gamma m, and so all the 3 quantities. So these are all non-negative. So you have this omega Q Gm square less than 1 by m, all the 3 terms are non-negative. Okay. So here I am using the hypothesis on Pij. Okay. So just remember these 3 inequalities, maybe star. So now we have this Gm in H1 omega equal to 1 for all m. So this is a bounded sequence, hence by compactness there is a subsequence. Okay, still we denote it by Gm, okay, such that Gm converges to some G in L2 omega. Okay, so this is by the compactness result. So every bounded set in H1 omega is relatively compact in L2 omega. Okay. And now we consider this. Okay. Consider this Gm Gk in H1 omega square. Okay. So this is so from the definition of the norm in H1 omega, so this is just sum of L2 norm plus the gradient square norm. So, this is just Gm minus Gk L2 omega square. So, maybe I will put this. Okay, so that is so this is absolute value. Okay, so just it is not triple norm. So, norm of grad Gm minus Gk square, that is in L2. Okay. So, this one we just keep as it is. So, there is no problem. In fact, that goes to 0 as Mk goes to 0, and this one. So, in fact, I will use less than or equal to. So, plus there are two terms. So, just we get del Gm square plus Gk by triangle inequality. Okay. So, this one I just again keep as it is. And now you use star. Okay, so, this important. So, all these three terms we have this estimate for all m equal to 1, 2, etc. Okay, so, this is 2 by gamma m plus 2 by gamma k. So, using star. And that goes to 0 as m and k goes to infinity. Okay. So, what does that mean? So, this implies Gm is a Cauchy sequence in H1 omega and hence converges. Converges to some G, and G is all it. Gm has already shown that it converges to G. So, that G has to be the same thing here, converges to G. Okay. And now, you again go back here, these three these three terms here, again you go back to star. So, that show that. So, now you let m to infinity in star by letting m going to infinity in star, we obtain. Okay, so, we obtain three things. So, this first one is grad G square is 0, second one omega q G square is 0, and last one R G square ds is 0. Okay. The first one implies G is a constant, and since norm of G is 1, in fact, this constant has to be identically equal to I think 1 by square root of the measure of omega. Okay, so that is not important. Okay. Since this is a constant, now look at these two. So Q is non-negative, okay, that is U, and R is also non-negative, and G is a constant here. So that means this integral of Q over omega is 0 and integral of R over del omega is 0, and since they are non-negative, so we obtain Q is 0 almost everywhere and R is also 0 almost everywhere. So this is on del omega and this is on omega, and that leads to a contradiction, because we are assuming both are not identically 0. Okay, and this contradiction proves that we have the other side inequality. So the triple norm and the H1 norm, they are equivalent. Okay, so that is an important thing, will be repeatedly used in the analysis of second order elliptic equations. Okay. So some observations. So now okay, just I will come again define this. There are three terms here. So for example, if we assume F and G are in H1 0 omega, okay, so then their traces are 0. So that is a corollary, if you want to call. So corollary in H1 0 omega this, just let me call it W1 Fg. So this is summation Ij Pij okay. This Q Fg. Okay, so the third term is not there because we are assuming traces are 0, induces an equivalent norm. Okay, so in the proof you just take, for proof take R identically equal to 1. Okay, so here again Q is non-negative. Okay. So in fact Q can be 0. Okay, so another corollary. So we obtain a important inequality. So in H1 0 omega, okay, so we take Q identically 0 and the matrix P as identity. Okay. So the Dirichlet norm okay, so let me just define that. Maybe I will put D here. This is not a standard notation, but I will just put it omega grad f square is an equivalent norm. Okay. So, that gives us one important inequality called Poincare inequality. So, this is one way of proving it. So, maybe we will see a different way of proving it. So, by this equivalence, what we see is for f in H10 omega. So, we have integral omega f square is less than or equal to some constant grad f square. Okay. So, again this inequality is very useful and will be often used in analysis of PDE. So, one can derive many more information from this equivalence of norms. Okay. So, I will stop here, and in the next class or perhaps in coming classes, so I will discuss this characterization of H10 omega. Okay. So, that is bit delicate analysis. I will do that in the coming classes. Thank you.